Yeah, then it's a great pleasure to welcome Amira today in our TML seminar to talk about their new paper that's on the screen. Yeah, Amira's a postdoc in Amsterdam at QSoft, as she said. And I guess we'll have questions along the way. That's all right. We have a soft deadline of 12 and a hard deadline of 12:30. And everyone, I guess feel free to unmute yourself to ask questions. Let's not do the chat thing. And take
Yes.
it away.
Yes. Cool. Thank you. Yes, thanks so much for inviting me to speak. I really, I like this group a lot. The research is always fun to read. And yeah, if you have any questions, just go ahead and ask. And I also look forward to hearing what you guys think about the work, because I think once I take you through the results, you'll see it's not really, I mean, what we do is not really so amazing. It's just like kind of connecting and rephrasing already a bunch of results that already exist, and like, kind of just making it clear, like in quantum machine learning, if you look at these kinds of models, we can't really ignore this problem of backpropagation scaling and how it scales compared to classical models. So this is like the main message, I guess. And this work started with, I was an intern with the Google team for a couple of months, and then some people from Caltech, Robbie and Robert, joined, and yeah, I guess it morphed into this paper. So long title, I didn't choose it, but yeah, basically it's a little bit about what backpropagation looks like for parameterized quantum models. And I gave this talk once before and there were 0 questions. So like, I'm assuming it wasn't a very good talk, but I'm hoping this audience is, because you're more QML, this maybe makes a little bit more sense. So let's see.
I wouldn't ask for it, yeah. Because that might end up in a different type of trouble, but never mind.
Okay, let's see. Yeah. Okay, good. So I don't have to spend a lot of time on the motivation of the problem, right? Because I think this is already pretty well known to everybody. So the types of models we look at are these parameterized quantum models, which we can just view them as some parameterized function that typically takes this form where we have some observable we care about, and we have some parameterized operations we apply to some initial state. And this comes up in like a lot of places, right? For example, quantum simulation, where you want to really simulate the dynamics of some system you're interested in, or learn some properties of a Hamiltonian or something like this. And but also in things like optimization, you want to encode very large combinatorial problems and estimate some solution to this. And lastly, of course, like quantum machine learning use these kinds of models a lot. Where the hope here, I think, is that maybe these kinds of parameterized models are interesting or more expressive. And I'm in no way advocating that this is the truth, but I think, a lot of people try and use these as a proxy for some sort of machine learning function. And yeah, I guess all I'm trying to say is that, in short, these models come up a lot in literature in different areas, and people seem to care about them. And if people care about them, then we need to be able to optimize them well, right? So we know we can optimize them, of course, but optimizing them well, and at least to a point where they're on par with how we can optimize parameterized models classically, I think is fair. So the leading way, I guess, people optimize these models classically is with gradient-based methods, right? So of course there are also like gradient-free optimizers and all these other maybe cleverer ways one can optimize models, but I think classically this is probably the best method. And so this is also the motivation as to why we should look at how gradient-based methods scale for these popular class of quantum models, right? So classical gradient-based optimization has been really revolutionary in the classical deep learning timeline, if you look at it, right? So even though we had neural networks, perceptron models, and so on for quite a while, it was really backpropagation, which I'll explain what it is at a high level just now, was really like, once we were able to optimize these models, could we now then achieve all these wonderful things we can do in classical machine learning, right? Where now we're at the state where models have, like, I think maybe even more than billions, maybe trillions of parameters in them. So it's like crazy sizes. And really, like the reason we're able to achieve these kinds of scales is because we can optimize these large models, right? So backpropagation.
Sorry,
Yeah.
Sorry, I wanted to ask, what's the height in this plot? I'm curious.
Yeah, no, nothing.
Okay.
No, there's no meaning.
Okay.
There's no meaning
Good.
to the height. Just yeah, my drawing.
Yeah.
Good. Okay, good. So at a high level,
right?
yes. Yeah, I guess so. Could be viewed as progress, or what is the closest in time to us, maybe. Okay. Yes, backpropagation at a high level, right? I mean, of course, we all know this. This is like a recipe to compute gradients of a function. And in terms of its history, it was really quite amazing because it was the first method proposed that was computationally efficient, right? And I'll talk a little bit more about this efficiency for neural networks. And I think what's important to say here about backpropagation, without going too deep into, like, you know, automatic differentiation literature and all this kind of stuff, I can get, you know, very hairy very quickly. But I think it's a little bit more than just a chain rule, right? So this is often kind of thrown in there that, like, backpropagation, the efficiency just comes from the chain rule, which I think is not really completely a fair story to say, because backpropagation, yes, exploits redundancy of structure in the function to compute gradients, but it also computes the function and stores information in such a way that's really clever, right? In such a way that you can reuse intermediate information for gradient computation. And this is how this efficiency comes about. So yes, it's two things. It's like exploiting the structure of a function. So it's like a white box approach. And then it's also making sure you kind of, you use, like, maybe some sort of dynamic programming to store and compute things efficiently. Okay, so now when we go to these parameterized quantum functions, things are a little bit more nuanced here, right? So this is just a toy example to kind of illustrate this nuance that I talk about. And again, I probably don't have to tell this audience this, but, you know, imagine we just have a very simple parameterized operation we want to apply to a simple model, right? So maybe we start with just one qubit and we want to do some sort of parameterized X rotation. So if we have the circuit, it looks something like this. And theta here is just like a scalar, right? It's just one parameter. And we can write the gradient of this with respect to this parameter of the state, like it has a very nice simple form. And let's say we want to measure some observable of interest, like maybe this is the Z operator. And so we can write our parameterized function that I, you know, spoke about in the beginning as this expectation value here, right? And so if this is our very simple model that we want to optimize, so we would like to compute the gradient of this thing. And so we can write the gradient out using the product rule quite straightforwardly. And this can also, like, we can simplify it as 2 times the real part of this first term here. And if we simplify this even more, let's say we want to evaluate the gradient at theta equals to 0. So we simplify this even more. Then we can write it as 2 times the imaginary part of this expectation value here, right? So okay, so if our function looks like this, and here is our gradient, and we know, like, you know, in the quantum setting, we kind of have to, like, sample to estimate these things. It's kind of okay because we're doing this for the function and we're doing this for the gradient component. And I mean, okay, in terms of, like, resources, we'd probably use the same amount. But obviously, as we start to add more parameters in this scenario.
Can I ask you a question on this?
Yeah, of course.
I mean, of course, that makes a lot of sense to estimate the gradient. I mean, if you look at the raw data that you get in these settings, then you kind of natively get certain elements of the gradient, as you say, and also elements or Hilbert-Schmidt scalar products of sparse matrices with Hessians, so second derivatives. Are you taking?
Yeah.
Are you taking into account second derivatives as well? Or do you even know of people using this somehow? Because, I mean, looking at the great, but I mean, like, literature in optimization is full of second order methods. and this is kind of strangely ignored in the field of classical control for variation quantum algorithms, and I wonder why that is actually.
So maybe you can explain to me what you mean by the data, and you mentioned something about sparse gradients or something.
No, I mean,
but,
if you just have a gate like this and have like a one parameter family, then from the data in the measurement that you
mean
get,
here, yeah,
you can, to my understanding, directly estimate certain elements of the Hessian. And then because of the trigonometric character of this, like e to the power of something, then there's no higher order derivatives that matter. Everything is a linear combination of first derivatives, which are the gradients that you specify, and second derivatives that are like elements of the Hessian. Yeah, I don't want to derail
so
this.
How would you? No, I'm interested. So how would you directly estimate the gradient when you're just doing this? Like, I mean, I don't see this. Yeah.
Well, I mean, I don't know. I mean, the question is like, I mean, this is your function, and the question is what like if you like given data on the right hand side, what derivatives of f can you estimate from data? And if you look at it, I mean, if you have a one parameter family of gates, as you say it, as you name it, then you can actually get second derivatives of this function as well by using data in the right fashion, by looking at the statistics of the measurement outcomes on the right hand side.
Okay, and you don't care about the scaling. This is just something you're saying you can get. Okay. Yeah, I mean, and your question is that why people don't care so much about second order optimization methods?
Yes, because I mean indeed, that's actually my question.
Yeah, it's a good question. I mean, in principle, this should be better. Yeah. In principle, this should get you to a minima faster, right? I mean, yeah, sure. I think people should in theory care about it. Yeah, exactly. So maybe okay, yeah, sure.
Yeah, go Amira if you want to.
No, please.
If I can chip in, I know a few papers that make use of the Hessian of these cost functions.
No, I know a couple of papers too. I mean, like for example, by David Wieris and others. I mean, there are, and also Andrea Mari. I know a couple of papers that do this.
So you also have a very nice expression for these Hessians in terms like you have a parameter shift rule to compute the Hessian, for instance. Like it's
exactly. In fact, even published about this. I mean, I don't want to print our own work. I mean, we have a paper on gradient rules in the setting. I'm just saying in the canonical reading of the problem, it's not often used. I mean, it's that's why I was wondering. But I know the paper by Andrea and by David and ours. I mean, there's at least 3 papers that look at this.
And some people actually thought that this would get you out of barren plateaus. But it turns out that when you have a barren plateau, you also have a barren plateau for higher order gradients. So not very useful for that, but maybe for something else.
And maybe it's just
can I also
maybe it's just a scaling method. Yeah, Johannes, sorry.
Okay, sorry. I mean, like I know it feels like 500 years ago, but there was a paper, I think it was called Quantum Analytic Descent, I think by Baldwin Coxor and some people. And I think this is kind of like the pinnacle of this idea, you can use the derivatives, because I mean, if you have this structure of like Pauli gates, then everything is kind of sines and cosines. And I mean, once you know like what sines and cosines you have, you know all the derivatives. Yeah.
Yeah, so that was my point, that you need first and second derivatives, and then the third order and fourth order derivatives can be computed from the first 2 because of the sines and cosines that just repeat forever.
Yes, and they make use of that by just saying, okay, if I know everything already, we can just like kind of go from here and extrapolate to faraway points and just like jump to better minima. And I think this is kind of like more or less the best you can do in this scenario when you say, okay, if you think about like higher order derivatives, these kinds of things.
Good, I completely buy it. Yes, fine. Sorry, we didn't want to derail this. Sorry, I this was more of a question that
No problem. Yeah, no problem. Yes, and maybe the research question that we asked will become a little bit clearer, because I think what we were trying to illustrate is we care a lot about resources to compute gradients, right? And then, I mean, then the question of higher order derivatives and estimating this using gradient information can come after, I guess, right? So, okay, cool, good, thanks. Okay, so yes, so with this toy model, what I just want to show you is like, okay, as we start adding parameters to this thing, again, we can write out expressions for the derivative of our model with respect to each parameter now, because now we've got two different parameters. And again, if we simplify and if we want to evaluate these gradient expressions and simplify by setting the parameters to 0, and I'll use this setting quite a lot throughout the talk, where like, you know, we have these gradient expressions, but then let's say we want to just evaluate them at the parameter set to 0. Then you've got like, you know, two different expected values that you want to estimate, right? And this is for each parameter. And so you can see, like, as you start, let's say you have m parameters in your model, this problem of like estimating m different gradient components corresponds to estimating, you know, m expectation values with respect to operators that don't necessarily commute, right? So this gives you like a little bit of intuition for like the nuance of the task. And also it's not so easy to reuse information in our setting, right? Because in some sense, when we do these measurements, we destroy our quantum information. So yes, so hopefully this like gives you a little bit of intuition why gradient scaling. So now we have to, you know, kind of estimate naively two expectation values for two parameters. And in general, what I mean by achieving gradient scaling,
in the number of gates, aka in the number of angles, correct?
Yes, so I'll explain exactly what I mean by how we count the resources, right? So there's kind of two ways. So scaling, yes, in terms of number of gates, but I'll define our cost model for that. And then there's also like an understanding of how memory should look as well. So backpropagation, the beauty of backpropagation classically in general is actually this ability to achieve a really, really nice scaling of resources in terms of time and memory. So if we're given like a parameterized function, and this can be anything, right? So like all we care about is, okay, the parameters, let's say there are m of them. And now we're interested in estimating the full gradient vector with respect to this function, right? So I'm using a little bit different notation here. F dash is the full gradient vector. So we want to estimate this to some precision. And so what backpropagation does is it says, okay, the time that it takes to compute the full gradient vector can be upper bounded by the time it takes to just run that function times some constant, right? So C1 is some constant. And the same holds for memory. So the memory it takes to compute the full gradient vector is roughly proportional to the memory it takes to just run the function itself. And for neural networks in particular, these constants are quite small. It's like a factor of 2 or 3. And so in terms of time, you can think of it, it's not so important really. I mean, it depends on the system you're looking at and you know, the types of operations you're doing. But you can think of time as like a way of just counting the number of operations, native operations, to compute the function and to compute the gradient. And yeah, I guess memory will also depend on the type of hardware you're using. But this is quite amazing, right? I mean, this relative constant overhead of resources is the magic of backpropagation, because this is saying, if you give me a model with possibly billions of parameters, I can compute the gradient with respect to every one of those billions of parameters in the same amount of time as just running the function once, right? So this is I think the crux of backpropagation scaling, and this is what I mean when I say you know, can these parameterized quantum models achieve such a scaling, right? This is the natural extension to this relationship that I'm showing here. Like, can we get this really nice relative constant overhead for computing gradients of these quantum models that I speak about, these parameterized quantum circuits? Yes.
For a deep neural network, wouldn't C2 depend on the depth of the deep neural network? Because to evaluate my neural network, I don't really need to keep the intermediate activations, right? I can just forget about them whenever I go to the next layer. But for backpropagation, I need to keep that, right?
Wouldn't C2 depend on the, I mean, C is just a constant, right? So do you mean?
So I just mean that when I evaluate a fit-forward neural network, from layer to layer, I can forget what was the last layer, right? All the last layers. I just need to keep the current layer to the next layer, right? But when I do backpropagation, I have to keep track of the evaluation of the fit-forward neural network at all layers in order to do backpropagation. So therefore, the amount of memory I would need for the gradient is depending on the depth. No?
Mm-hmm. Yeah. I think there are probably more, maybe more sophisticated. Yeah. Okay. This is true. Yeah. Yeah. I don't know. I think so. So in general, this relationship can kind of be stated for maybe like a very sort of unsophisticated method. I don't know like if the C2 should have scaling with the depth. I don't see it. I don't know.
Yeah, maybe there is a more smarter way to do it to keep the memory low, but okay. I didn't see that.
They must be right. I mean, and admittedly, I also don't know much about how this how deep the memory scaling goes, because it gets very computer sciencey and goes into like, you know, a lot of assumptions about the hardware that one uses here and the structure of the function. But I think if you just yeah, I don't know, maybe we can see after. But I guess for the purpose of the discussion, it's also not so important, because what I will show you is that this one here, time, is very difficult to achieve. And even when we so the whole story of the paper is, I think we present a method that achieves this roughly, but even though it does, it requires exponential classical memory, so we still won't achieve this anyway. So okay, good. Yeah, sorry, I don't know about this, with how to include depth here. Okay, good. So okay, so the question is like, can we achieve this relative overhead of resources for quantum models, right? Because we know classical models can exhibit this, and in particular, like we try to investigate the question by even relaxing a little bit these constants and saying, okay, let's allow them to have some sort of vague dependence on the number of parameters in the model, right? So m is the number of parameters. So even if we say like, we want this relationship to hold and C1 and C2 can scale polylogarithmically with m, let's say, can we achieve this? And this is the research question that we investigate. And yes, as I was saying, what we show in a nutshell is that indeed we can get this kind of relative overhead in time, and I'll tell you what constitutes time in this cost model. But yeah, our approach that we kind of put forward, unfortunately, requires exponential classical memory. So this is the downside. And also, like, just off the bat, something important to highlight is that all gradient methods in literature right now do not achieve this relationship, right? They achieve something worse, which I'll show you in the next slide. So this is something I think that's quite important, especially for like new students coming in who are very excited to, you know, do quantum machine learning, and then they want to train their models and optimize them, and then, you know, you kind of very quickly see when you start doing numerics that this is not so easy to do, right? Things take a long time. So okay, so let's talk about the cost model, and in particular the cost model for time, how we count these things. So we make the assumption that every parameterized operation that we apply in our circuit and its inverse is unit cost, right? So if we have, let's say, some u of theta where it's just like a product of parameterized operations and there are m of them, then each of these things and their inverse costs us 1. So if we're given some state rho, yes, is there a question? No? Okay.
No, I think it was an echo. Sorry.
Okay. Okay, cool. So if we're given some state and then we apply parameterized operations to them. And then remember our, okay, so we apply m of these. So this will like, kind of cost us roughly m to set up this state. And if you remember, our model of interest is just like, we're interested in some observable O. So to estimate our function, right, this will cost us roughly m operations, of course. And then typically we assume we, sorry, can somebody, I think, is unmuted?
Yes, I think Junior, can you mute yourself, please? Thank you.
Okay, good. Thanks. Okay, so yes, so we want to estimate usually our function of interest, right? And typically we sample here to estimate this with like some precision. So yeah, I just put like epsilon squared or whatever, but really this is not so important for the discussion. We can just assume some sort of measurement scheme, and it estimates the quantity of interest with some precision. Okay, and so like for simplicity, if we just assume that we know what the state rho is, and we can write out again our expression for gradients, right? So this is the gradient of our function with respect to the kth parameter, and it looks, sort of similar to the model itself, but there's like a partial derivative in there. And so if we try to estimate this in terms of this cost model, again, we would be like applying m operations to do this and sample as well. So this will roughly cost us m as well. But the catch, of course, is that this is just for a single gradient component, right? And so if we had to do this naively for every component in the gradient vector, then we'd have to do this m times. So we'd get this like m squared scaling for the full gradient. So in terms of like, this relative overhead that I presented earlier, the time then to compute the full gradient vector scales like, m squared, which is something like m times the cost in time to just run the function, right? So if you remember, classically, we have a constant here, right? These things are roughly equal. So now the task is to try and find a better method to get rid of this like this quadratic scaling, right? To try and get something just like linear. And you might think this like quadratic to linear reduction is not so big, not such a problem, but in reality, in terms of classical machine learning and stuff like that, it really is, right? So here's just a picture of if we could achieve, true quantum backpropagation scaling, then that's the green x's, and the red x's are I think a popular way to compute gradients of parameterized circuits currently, this parameter shift rule. And the parameter shift rule exactly has this m squared scaling that I speak about. So this like, kind of bad scaling. So you can see like, if you have a day to train a model, you can compute gradients with respect to a model that has 9,000 parameters with the parameter shift rule. That'll take you a whole day. Whereas if we had backpropagation scaling for our parameterized quantum circuits, we can start getting into the millions. So really this, I think, yeah, this is important, and I think classical machine learning people would agree, because things like kernel methods, I think, have quadratic scaling, and people don't use them in practice because you can't optimize them as fast as neural networks, right? Okay, good. So there are a couple of settings that we consider in the paper, and depending on which setting we are in, we can make already some statements and borrow from results that exist in literature. So the first setting is the most general, right? So it's imagine that you are given you're given states that are unknown to you. So we call this like the quantum data setting, because yeah, you're given some copies of your state and you don't know what this is. And then of course the second setting is that you can imagine your state is given to you and you know it, right? So you know how to construct it, or you know it explicitly. And then within these two scenarios, we apply parameterized operations as usual, and these are the things that we like count in our cost model. And yeah, and then our function, yeah, looks like this. And then we are then in a further kind of assumption of, do I have single copy access to the states that I'm given, or can I measure like a tensor product of them all at once, right? So these are the kind of, I guess, 4 scenarios. You can assume your state is known or unknown. And within those 2 regimes, you either have single copy or multi-copy access. Okay, and hopefully it will be clear which scenario we're in when I explain the results. Okay, so there are a couple of things we can immediately say. So if we are in, for example, this quantum data setting where we totally, rho is arbitrary and given to us and we don't know what it is, and we can only measure single copies at a time, then we can immediately use a result that tells us that this backpropagation scaling that we want is not possible in general. So this is a bit of a bummer, but like, and a way to see this is we use a lower bound that comes from this paper here. And how to see this is we kind of simplify our model a little bit. So let's imagine that the observable that we were interested in is just the identity. And the parameterized operations that we apply in our model are just like Pauli's, right? So they're Pauli operators acting on up to like n qubits, if you know that's the size of your system. And so now how to use the lower bound is to say, okay, well, firstly, let's write out the gradients and again, use the simplifying setting where we set all the parameters to 0. So we write out the gradient expressions and we set thetas to 0. This actually just reduces to estimating expectation values with respect to Pauli operators. So the ith gradient component it corresponds to like this pi operator here. And so this task of estimating expectation values with respect to Pauli's, if we consider every possible Pauli operator we can apply in our model, and if there are n qubits in our system, then there are roughly like 4 to the n of them. So we take our number of parameters to be roughly 4 to the n. We want to estimate every possible pj. Then we can use this lower bound from this paper that tells us how many copies we would need to achieve this task. And the number of copies that we need is like, basically, tells us that the scaling scales pretty badly. It gives us this m squared, this quadratic scaling that we don't want to see, right? So this immediately tells us, okay, so it's not, in general, this is not possible to get the backpropagation scaling we want. But interestingly, this result does not hold under an additional constraint of if your state is unknown to you, but it's guaranteed to be a pure state of polynomial complexity. So if you now imagine rho is
you're saying that the theory, I mean, this quantum memory is like the kind of an obstruction against like using single copies and like having exponential overhead when you use one copy and you can efficiently do it with more copies. You're saying that this obstruction is not applicable if you add promises to your state. Is that what you're saying?
That's right, yeah.
Wonderful.
That's right. Okay, but then unfortunately, there's still some like computational hardness statements you can make about trying to get this backpropagation scaling. So let me try and explain the intuition here of why. So now imagine you have this promise, like Jens mentioned, like that your state is pure and it's guaranteed to be generated of a circuit of polynomial complexity. So polynomial complexity, I mean like you have a fixed gate set and the number of operations it takes to create the state scales polynomially in n, right? Where n is the size of your system. Okay, so if you have this additional constraint, then you can actually explicitly learn this state. And a way to see this is quite convoluted, but basically you can learn the state with an efficient number of measurements if you just use classical shadows and a really dumb like search procedure, which I'll explain in the next slide. But unfortunately, this procedure that we kind of put forward to learn the state is not computationally efficient. So in general, we still can't like get backpropagation scaling. So it's a little bit of a weird result because it says, okay, we can like, if we have this promise, we can learn the state explicitly, but we can't do it computationally efficiently. So let me explain why. So if we have this promise, right, then we can kind of say there are roughly k possible circuits where n is number of qubits and p of n is just some polynomial in n, right? So this is still exponential in n. There are exponentially many possible circuits that our state can be generated from. And now what we can do is we can and let's denote every possible state created by each of these k circuits as phi, right? So phi 1 to phi k. These are all possible states we can create with these k different possible circuits. So there are exponentially many of them. But we know we can use classical shadows to estimate the fidelity with respect to all of these states by creating like, this shadow of rho. And so we can estimate basically, all these quantities, all the fidelities with just a number of measurements that's polynomial in n, right? So this is efficient. We can do this using this classical shadow scheme. And since we have the additional promise that our state comes from one of these circuits, we know that with high probability we'll find a match of like, perfect fidelity. We'll be able to determine what the circuit is that produced our state. But obtaining the maximum fidelity involves, storing exponentially many values and searching over them, which if you do this naively is very clearly computationally inefficient. And so we thought, okay, maybe there can be a way in which you can identify the state in polynomial time, so a way that is efficient. But unfortunately, this also cannot be possible in general. And the way to see this is to just consider the class of pseudo-random quantum states, which is not, the details are not so important, but basically there are some hardness proofs that show that there's no efficient way to distinguish these pseudo-random quantum states from Haar-random states, right? So these states are shown to be computationally hard to learn. So since these pseudo-random quantum states are actually states of polynomial complexity, then, with like some standard cryptographic assumptions, we should not be able to, in general, identify a state in polynomial time using this classical shadows procedure. So this whole story is not really so important. It's kind of tangential. I just included it because I think it's interesting. But basically, what I'm trying to tell you is that to get the backpropagation scaling we want, it seems really unlikely if we are just given single copies, right? So as a summary, if the state is completely unknown to us, then information theoretically this is impossible, right? So this is like a no-go statement. If the state is unknown, but we have this promise it comes from a polynomial complexity circuit, then it seems computationally unlikely. And this is through like the pseudo-random argument. In general, of course, there could be specific. Yes, hi.
Can I make a question? Sorry to interrupt you.
Yes, of course. No, it's fine.
You mean computational unlikely because we don't know if there are actually pseudo-random states or what? Like,
yeah, exactly.
Why computational unlikely? Okay, so if there are pseudo-random states, then that's true. But we believe that there are. So this is the reason.
I think. Yes, maybe I clarify. So I think I'm just trying to make a statement in general, right? So so in general, this class of states belongs to this family, and so in general, it will be kind of there's no like kind of blanket approach to solve this, right? So but of course there could indeed be like specific class of states that are still like it's computationally feasible to identify them or learn them. So maybe this helps clarify. Yeah.
Yeah, I also have a question, if you don't mind. I can kind of follow the argument after you define the cost function, but this specific cost function that you take, why is it not constant? Is it not just a trace of a quantum state?
Yes, okay, that's a good question.
Why its gradient is not
you mean this?
zero?
You mean this one here?
Yeah, so that's a gradient, right? So
yeah.
The cost function itself
exactly.
is the trace of a quantum state.
Yeah, exactly. So I think what we're trying to say is like before you like set the parameters to 0 to create the circuit itself, one still has to like run m operations, right? So like if you kind of like set it to identify. So how do I explain this in a manner that makes sense? So so you're saying this here doesn't cost us anything because we're just estimating directly these Paulis, right? This is what you're saying?
No, I mean, what I'm saying is look at the cost function above it. This is the trace of a quantum state. The f of theta is just trace of a quantum state, right? So it's whatever theta I put in should be 1, no?
The U and U dagger cancel.
The U and U dagger
okay.
cancel.
Yeah. Because of the cyclicity of the trace.
Sure. And this is 1. Whatever theta I put in, this is 1. Why would my gradient be non-trivial for a constant function?
Well, I mean, if you just write out the gradient expression, right, you get like a partial derivative here, and then it reduces to like, you get like a Pauli operator drop down, right?
Mm-hmm. I can see
so
that,
it's not so straightforward.
but I cannot see it from the fact that this function is constant. And therefore, you know, its gradient should be 0 everywhere if it's constant everywhere.
Yes, I think I agree with Sofian. Like the moment you said O equals identity, then f of theta would not depend on theta. It would depend.
Right. Okay.
It could depend on
fine.
rho if rho was mixed or something, but so the gradient should be 0 everywhere for every component.
It's a constant function, so it should have a 0 gradient. I mean, this is, maybe I'm missing on something here.
No, maybe I am, right? I mean, if you just write this out, like you just put, and then you write out the partial derivative with respect to like just one parameter. I mean, you know, you kind of get the PJ drop down, or minus I PJ drop down.
That's true.
Yeah.
And yeah, I'm sure. Okay. I guess I have to look into the math and and convince myself that this thing can have non-zero gradients. You know, like,
yeah.
Okay.
Okay.
But this is not the main message. Yeah. Anyway, thanks. I'll look into it later.
No, sure. Yeah. Okay. Good. Okay. Yeah. And I mean, this. Yeah. There's this possible like there's mistakes here, right? So it's good that you ask. So okay. Good. Okay. Perfect. Where were we? All right. So yes. So the message, I guess, with this idea of single copies is if we're totally unknown, we don't know the state, we know we can leverage like sample complexity results that like tell us, okay, we won't get the scaling we want. And yes, we spoke about this computational stuff. And then in the paper, we kind of outline, okay, well, what if the state is known to you completely, right? Which is typically common in, at least in these small quantum machine learning setups. And there we kind of just like iterate through all gradient proposals and just show that like, again, it seems computationally unlikely because all these current methods to compute gradients don't achieve the relative overhead that we want, right? So, okay, so now in the last couple of minutes, I just want to talk about the obvious next thing to do, right? Is to now allow for quantum memory, so allow multiple copy access to your state. And then can we do better? So especially drawing on like some of the success stories of these 2 copy measurements and it seems that we can now like unlock things that we can learn, functions we can learn that we can't necessarily learn in the same amount of resources classically. So if we allow this additional functionality, can we do better? And indeed, in this like restricted setting, where like I kind of assume that these Paulis are the operations we want to apply, we can immediately use a scheme that comes from this paper here that tells us that we can estimate our gradient components, which is just like these Pauli operators, by just using a number of copies that scales logarithmically in m. So if you remember, like our definition for backpropagation was we wanted, ideally a constant, but maybe even something that scales like logarithmically or polylogarithmically in m. So we can do this with the scheme coming from here, where they just like kind of use 2 copy measurements to estimate the magnitude of the gradient values or these expectation values. And then they do like a majority vote scheme to estimate the signs. So this is nice and this is promising. But unfortunately, as we start to like move to more sophisticated ways, right? Because I mean, you're right, like setting this to identity doesn't necessarily make sense. And so once we start to move to more sophisticated settings and theta shifts away from 0, this scheme that works here does not work anymore, right? So this scheme like explicitly takes advantage of like special properties of Pauli's and so on. And so when we get to like a little bit more sophisticated models, then the scheme breaks down. And so yeah, we spent a lot of time trying to understand why and to try and find something that works. And then like we stopped to think, okay, well maybe there's something deeper going on that prevents us from like getting this scaling that we want for backpropagation. And so in the more general setting, what we were able to show is that there's actually a connection between this problem of estimating gradients and the problem of shadow tomography. So So I'm sure, like, most of you are familiar with this shadow tomography idea. I'll just tell you the high level problem again. So the shadow tomography problem is actually quite cool, right? It's like, you imagine you've got like a bunch of 2 outcome measurements that you're interested in estimating with respect to some unknown state that you have. And the idea is you want to output estimates close to this true expected value that you're interested in with respect to all these measurement operators. So you want to output estimates that like tell you that are close to the expected values you want with respect to these measurement operators, but you want to do this in a way that's sort of resource efficient, in that like you're allowed copies of your state, and you want to see, okay, how many copies do I need to perform this task, right? So what is the minimum amount of copies I can achieve this task with? Like, so then, right. So m is the number of copies here, just for notation, like little m, and we want to minimize this, right? So this is the problem of shadow tomography, is I want to estimate all these expectation values with some precision, and yeah, how many copies do I need to do this? And just a little bit of a further definition, because I'll make reference to this this observable just now, is we call in the paper like a polytime observable, basically just something that takes on this form here, where like Z1 is like measuring Z on the first qubit, and U is just like some fixed circuit. Okay, so we call these operators like polytime observables. Yeah. Okay, and so the reduction that we have is just basically the following. So if you imagine you have an algorithm to compute gradients with some precision, and that algorithm takes m copies, little m copies, and has a certain runtime, then this algorithm will also give you an algorithm to solve this shadow tomography problem with respect to polytime observables with the same runtime and the same number of copies. Okay. And how we show this reduction is we define a little bit more of a general model than what I spoke about earlier, and we call this a quantum neural network. And we assume that as input, this quantum neural network model takes some unknown state that's given to us, and an additional, we attach an additional qubit to this. And the variational circuit is quite straightforward. It's basically, again, like you can assume some parameterized operations, but interspersed with fixed circuits. So these U's are just like some whatever you want, like just some fixed circuits between the parameterized operations. Okay, and so our quantum neural network model looks very much, similar to the models that I've been talking about, but we measure like first qubit in the Z basis, and we apply this variational circuit. And so the gradients also take a very similar form when you set the parameters to 0 or whatever. Actually, it's just 2 times the real part of this expected value, which looks very similar to the function, right? It's just there's a partial derivative in there. Okay, so taking the gradients of this quantum neural network, one can then like write out make some assumptions on the operations and like show basically that things cancel, and ultimately what you're left with is estimating these expectation values with respect to these polytime observables here. So the details here are not so important, but basically this just in a simple way kind of relates. If we wanted to estimate gradients with respect to this model, it corresponds to the shadow tomography instance where these EKs are these polytime observables that I spoke about earlier. So this is like the connection. And so now I guess a nice thing would be like, okay, well, shadow tomography is like a super well-studied problem in quantum information theory. And what can we use from there to perhaps try and make the gradient scaling or backpropagation problem more efficient in some way, right? So the last thing that we do is we like propose a quantum efficient backpropagation scheme by using shadow tomography protocols. So in doing so, we can basically come up with a method or an algorithm that estimates all of our gradient components with a scaling that is linear in M. So to my knowledge, this is the first proposal, I think, that achieves linear scaling, at least in the way we define cost, right? So we get like okay, it's quasi-linear, right? Because it's like there's a polylogarithmic dependence on M, but we kind of we kind of get in line with this backpropagation scaling that we want, because we can borrow from shadow tomography protocols to estimate gradient components. But there is a huge caveat here, because the method that we propose and the shadow tomography protocols that we use all rely on classical storage that scales exponentially in the number of in the system size, in n. So this is unfortunate, and this in general is not possible to get rid of unless we want to, like, violate some very standard assumptions about complexity classes and things like this, I think. So how the approach works in a nutshell, if I have time, I think I do. Sorry, I know that I also want to leave time for questions, but
we're very good on time.
Okay, good. Yeah, so this is the last thing I'll say. Just here's a snapshot of this this quantum efficient backpropagation algorithm, which just pieces together already like existing things, right? So admittedly, I don't even really know so much the deep details of, for example, some of the components, but one can just piece together the results here to show a couple of things. So okay, so let me start with what's happening here. So we combine two things: online learning from the paper of Scott Aronson and a few others, with something else called a threshold check, which comes from the second paper with Ryan and a couple of other people. So the exponential storage cost, like the classical exponential storage cost, comes from the fact that we initialize this online learning algorithm. And sigma here is basically, you can think of it, it's called a hypothesis state. So it's like a guess for your actual state, right? So rho is your actual state. So we have sigma. That's a guess that we store in classical memory. So this is like a 2 to the n by 2 to the n matrix that we store in classical memory. And we use this this guess to basically check if the expectation value we want to estimate is close to our estimate with a hypothesis state. So like we do this threshold check at every measurement step. So we want to estimate like m observables. So at every observable step, we do this threshold check where we say, okay, using our hypothesis state and the observable of interest, is this estimate for the quantity we want, like in our case, the gradient, is this gradient estimate close to the true estimate? And we can do this threshold check in a manner that does not destroy our copies of our quantum state. So this is the beauty of this this procedure. And let's say, okay, cool, they are close, then we can proceed to the next observable. So if they are close, we can proceed. And here is also the magic of why this is a little bit different to standard shadow tomography protocols, is because of the structure of our neural network, we can apply rotations to the next kind of layer in the network, if I can use this word layer, probably incorrectly. So we rotate our quantum states in memory by like one parameter update. And then we perform the same procedure again, where we check, okay, like now we want to measure the next gradient. And we check, okay, is the estimate using our hypothesis state? Oh, we also rotate our hypothesis state in classical memory, right? So we check if our estimate for the gradient with the hypothesis state is close to the true estimate. And again, we can do this like gently using this threshold check. And gently, I mean like you don't disturb these copies in memory. If they are far apart, then indeed we will disturb these copies and we must actually measure them. And so this algorithm, strictly speaking, works in batches of rows. So if we have to destroy and measure, then we destroy the batch and we need a fresh batch. And so then one can kind of like bound how many mistakes you would make and what the resources look like to
I mean,
ultimately
the
get all
proof of the guarantee is in on the sample complexity. We'll take this into account, like how many times you will have to.
Exactly, yeah. Mm-hmm. Yeah, exactly. And then yeah, just going back, so here is the best sample complexity, I think, for shadow tomography at the moment, and we kind of just use this. Okay, good. And then like lastly, we kind of considered, well, trying to remove the classical offline model, right? Because this is where like things kind of suck, because we'd have to store this hypothesis state in classical memory, which is like quite expensive. And so the last thing, I don't want to talk too much about this because it's not really important for the message, but the last thing we show is that if you try and just do a fully gentle approach, then you like violate some known query bounds, and yeah, things get all a little bit weird. Okay, so yeah, so I'll leave with just a couple of open questions. So the first is like, it would be really nice if, for example, I mentioned this shadow tomography instance with respect to polytime observables. So far, there is no known, efficient procedure for this, classically efficient procedure, I should say. But maybe there is one, right? Maybe there is a way, just like there is a classically efficient way to do it for Pauli's. Maybe there exists an efficient scheme for these, just for this class of observables, which would then allow us to estimate gradients for an interesting, quantum model, parameterized quantum model. Perhaps there are like better ways to store these hypothesis states in memory, like to approximate them. Maybe there's a way here to do this efficiently classically. So this would also help. Maybe there are also like, other special cases of or class of circuits or models that seem to work or that are trainable. Or perhaps it's just time that we have to try and maybe consider other types of models, especially in quantum machine learning. Or maybe more sophisticated ways for optimizing. Maybe there are some gradient-free approaches or something like this, where this implicit scaling is not too bad. Yeah. Okay. Good. Thank you very much for listening, and thanks for inviting me. I always like to chat to you guys. The last talk I gave was a couple of years ago, but it was a very nice experience. So thanks a lot.
Thanks.
Thank you very much. It was very, very nice, I thought. Yeah, we should still have some time for questions. Now, up to us if we want to do a chaotic sneak attack approach or raise hands and things. So let's make a test. Would anyone like a sneak attack? Assad, you can not sneak attack.
Hi, thanks, Amira. I was wondering, as for the complexity of the shadow tomography algorithm, I was wondering that this scheme that you have, it's restricted to polytime observables, but the dependence on epsilon is still worse than the general O'Donnell dependence, right? It's, I think they have E squared.
Do they have epsilon squared?
Yeah.
Is that right?
Yeah.
Okay.
So, yeah.
Are you sure? Maybe I have the paper open. Let me. Sorry, I just want to stop checking because I thought. Let me have a quick look. I mean, you're probably right. Let's see. No, this is epsilon 4. Yeah. 4.
So, I just opened up the archive version. It says epsilon squared in the abstract.
Okay. So maybe I'm looking at
Actually, yeah, you're right. Yeah, you're right. I think I would say
as well.
Yeah.
Okay.
And then the idea that you have for this sort of hybrid approach, so you basically take a batch, do online learning, and take a mistake bound from online learning that's caught it all have. And basically say that you can make at most probably many mistakes in this batch, and then you basically go to the next batch and so on and so forth. And you have a number, like bounds on the number of batches, kind of.
Yeah, exactly. Yeah, we literally just, exactly, yeah. We just take exactly what they do. And the only difference really is that between each measurement step, we rotate our copies in memory and our hypothesis state. That's the only thing. Yeah.
Right. And then why is the poly observable restriction necessary? Because these two protocols are independent of the type of observables that you.
Yes, this is not necessary in the algorithm we proposed. It was just for the reduction.
Okay, thanks.
And in your quantum backpropagation algorithm, I mean, you're basically going from m squared to m because you reuse things when you compute the gradient.
Exactly.
Right?
Okay. Yeah, exactly. And I think what's nice is it's a little bit subtle also because it's not just it's this rotation in between measurement steps that really allows you to reuse the structure of the function in a way that's very similar to what happens in classical neural networks and classical backpropagation, right? It's this information reuse, but also the structure. So you're reusing information, but you're also kind of making use of this like white box approach, you know, which backpropagation is inherently white box. So I think that's like yeah, a little bit of a cool thing.
Good.
Of course, I'm biased. Yeah.
You're free to find your own work. Cool. No.
Good. Any more questions? Antonio, I saw that.
Okay. No, I'm a bit okay. I'm sure about the question. Like, can you say what are the downside of your algorithm? Like you said that you would need the exponential computational time or resource or what? Like.
Yes, I mean, so if m, like the number of parameters is exponential, this approach, you know, it takes one observable at a time. So this would take exponential time, right? So that's, I mean, that's I think unavoidable. But I think the real downside is that we have to have this hypothesis state in memory. That's the main problem. And I think, you know, this is also a problem for the shadow tomography people, but maybe not necessarily. I mean, in instances where, you know, the classical cost is cheap for some reason, or like, you know, you view it as cheap in your overall task that you're trying to solve, maybe it's not such a big problem. But yeah, I guess, and there's no way, unfortunately, to get around this in general, this having to store this. But there could be special cases or instances that, you know, models are still expressive or interesting and maybe don't cost you as much. Maybe you can efficiently approximate your hypothesis state offline. So this is something I'd like to look into.
Okay, thank you so much.
Oh, cool.
Any other questions?
Good. So, yes, I have one. So, when are you going to invite me to visit the group in person? You know, when I got the invite to the seminar, I thought, oh, I can come visit in Berlin, but not so.
Oh, anytime.
That's a very good one.
It's totally your fault that you're not here.
No, I guess it was my fault.
No,
we'll make it next time.
I'm joking, but come around. I mean, the connection is very good. I mean, Amsterdam is really close. I mean, you can fly, but even the train connection is not so bad.
Yeah, it's not too bad.
It's much better than the reputation, as I said earlier today.
Good.
Yep, but noted.
Yeah.
If there are no other questions, I have a change of gears question, which might not come as a surprise to some. Okay, so we've been having some discussions in group about this unknown quantum states. Like unknown quantum states exist potentially, you can talk about them, but me personally really struggle to find a realistic supervised learning task where you would have unknown quantum states. So question one, have you thought about this? Question two, could you give me like any thoughts you have on realistic supervised learning task where the input data is essentially unknown quantum states?
Yeah, no, sorry. I mean, I agree. It's and also I'm not you know, physicist, so I think maybe the intuition comes a lot from physics. And so Jared, who I started working with, unfortunately, you know, I usually ask him to join me in all these calls, but the time zone for this one wasn't possible. But I think he's got a lot of intuition behind where these quantum data settings could lie, and it's something I know that they're thinking about a lot. So maybe if you want to know a bit further, we can just ask him, because I think he's given a lot of thought. But yeah, to me, I'm with you. I don't really know of any scenarios.
Okay, cool. Thanks.
Sorry.
No. I mean, I just attack people, and so far your answer is the one I've been getting, which kind of proves my point to myself. not that I need to prove anything to anyone.
Okay, but I
this
wouldn't
was
take
helpful.
my opinion. I wouldn't take my opinion too seriously. Right? I think maybe us, like probably a bunch of physicists, they may be
Yeah, I will. Thank you.
Sure.
Okay, very good. Any other questions? Okay, then we can wrap it up. This was very, very nice. As Jens said, we usually cut the discussion out of the recordings and we can show you the recording and then we decide if we make it public on YouTube, private on YouTube, or private not on YouTube. So, but
I'm happy to make it. I'm happy to make it public. Yeah, I don't think I embarrassed myself
Okay.
too much today. So I guess that's okay.